The next talk is about another instance of co-simulation, this time between TVB and the neurorobotics platform. We're going to show you a demonstration, technical demonstration of a virtual body co-simulation. And I give the word to Christoph to first take you through an introduction to the NRP platform. And I'm going to change the slide. Yeah.
Yeah, so as Denisa said, I will start with a short introduction to the neurorobotics platform, or NRP in short. So NRP is a set of software tools that allow us to prepare, execute, and monitor simulations of virtual agents that interact with their environment in a closed-loop manner. So basically, NRP allows us to bring the fields of neuroscience and robotics together, and both of these fields can profit from that. So embodied agents like robots can use neurocomputational models or neuromorphic tools in order to gain situational awareness, become more adaptable, or able to generalize, well, in essence, to become more intelligent, let's say. And then neurocomputational models can be refined and improved based on the inputs from the virtual environments. And by using embodied agents, we can reduce the need for use of live animals in the experiments. And we can also innovate faster in the fields of neurorehabilitation or in neuroengineering, for example. Next slide, please. So the main features of NRP version 4.0, which is the latest version, which is currently being released. So this version of NRP would emphasize on modularity and parallel execution, and it provides support for containerized environments in which different modules of NRP can work in. The modules are arranged in a spoke hub architecture with a so-called NRP core as the hub and distributed engines or simulators. The communication between modules, basically between NRP core and the simulators, is using the client-server communication paradigm. So basically, the simulators are services to the NRP core or the orchestrator. And all of this makes NRP highly distributable, and it can be deployed on a single PC or office cluster or even supercomputers. Next, please. So the main working mode of NRP are fully deterministic simulations where simulators use fixed time increments, but we also support soft real-time or event-based simulations. And many popular simulators are already integrated with NRP. So, for example, simulators like Unity, OpenSim, Mujoko, or TVB. And we also have support for neuromorphic hardware, such as Spinnaker and Oihi. Next, please. So the two main building blocks of an experiment in NRP are engines and so-called transceiver functions. So one engine is a simulator of your choice and some code that allows it to communicate with an NRP core and basically to act as a service. We support the different communication protocols between the client and the server. Currently, we have implemented protobuf over Google Remote Procedure Call and JSON over REST. And different engines can run at different time steps, and simulation steps for all engines are executed in parallel. And transceiver functions are basically adapters between simulators that allow us to process and convert data coming from one simulator into something that other simulators can understand. And these are user-defined Python functions for convenience. And yeah, this is it. Next, please. So in the current experiment, we have two simulation engines. We use Gazebo engine for physics simulation and the TVB engine for the brain simulation. And we have two transceiver functions that translate the data flowing between the two engines. So at the every time step, Gazebo engine outputs a set of positions of finger joints, which are translated into proprioception that is an input to the sensory region in the TVB engine. And within the same time step, kind of in parallel, The TVB engine outputs a motor command that is translated into position references for the finger controllers. Yeah, that's it.
So I will introduce the specific simulation and model we use for demonstration. It is built on an experiment that is very well known in human movement science. It's an example of a phase transitioning by manual coordination. And there is a model that has shaped the relevant literature, the Haken-Kelso-Bunz model, published in 1985, upon which we are also going to build. So the experiment is about people moving their fingers, and it has been shown that if they start with the antiphase or parallel mode, where fingers move left or right at the same moment, and if they start moving faster and faster based on a metronome, at some point they make an involuntary transition to the in-phase or anti-parallel mode, where when the one finger goes left, the other goes right. It's a bit like this. So this happens, as I said, involuntarily, and it shows that there are two modes of coordination, the antiphase and the in-phase one. And as the frequency goes faster, the one destabilizes and only in phase is possible. The opposite thing doesn't happen, so there is hysteresis. If you start with in phase, no matter if you go slow or fast, you never transit because it's a more stable mode. So in order to implement this, we use the equations from a later publication by Yirza, Fuchs, and Kelso, where brain was also involved in a brain and behavioral system. We use the equations you see here on the first panel. Its equation is a two-dimensional oscillator, and there are couplings between them through the parameters alpha and beta. And this is a coupling of both velocity, which is the x1 and x2 parameters, position, the x1 and x2 parameters, as well as velocity, which are the x1 dot and x2 dot parameters. Now, the specific characteristic of these oscillators that facilitates the transition is that they have a specific relationship between amplitude and frequency of movement. And amplitude actually decreases for increasing movement frequency. And this has an effect that there's specific critical amplitude, which corresponds to a critical frequency. And there is a transition, and antiphase mode loses stability. And as amplitude and frequency are related, this happens for a specific value that is determined by the coupling between the two fingers. So in order to implement this, we form this task dynamics where we focus on 4 brain regions, the 2 motor cortices and the 2 sensory cortices, which for each one of them, we use one of these equations, as you can see here, and we couple them in the following manner. The left motor cortex provides a motor command of position and velocity for the right robotic finger. The same thing happens on the other side. And then there is also proprioception from the right finger towards the left sensory cortex, likewise on the other direction. And finally, there are interhemispheric couplings from each sensory cortex to the motor cortex of the other side. The robotic fingers are modeled by the gazebo robot based on PID controllers, which are oscillators actually of this almost the same kind, but without this specific dependence of amplitude and frequency. So the transition cannot be initiated, in other words, by the fingers themselves. It has to happen in the brain. And we form the connection matrix based on this task network with all weights fixed to 1 and by discarding time delays for the moment. All these parameters have some range where the result wouldn't change, but we're just showing you here a demonstration. And we embed this network now to a full normative brain connectivity. And we do that by somehow suppressing the rest of the connections. So we first normalize them, and then we apply some factor to reduce their importance compared to the task connections that you see here that are being stronger. So all this model now from the TVB side formulates what Christoph called an engine to be linked to the NRP core. So this TVB engine consists of the model itself, which is a new model we created for TVB, the HKB brain model. And then also we need to set up and configure the co-simulator. By the way, this co-simulator is the same co-simulator used more or less also in the TVB multiscale toolbox that you showed before. And all these configurations are taken care in TVB multiscale behind the scenes. But here we had to explicitly set them. So we had to increment the TVB connectivity with the two fingers, which are something external to the brain, but internal in the end of the day to the TVB connectivity. And therefore we need to define here the indices where these two fingers are and where TVB has to send or get data from. We identify the state variables, x1 and x2, more or less position and velocity that are implicated. The synchronization time for data exchange between fingers and the rest of the brain, which we set now to be for every TVB time step. We define a co-simulator monitor that will record the TVB data to send them to the fingers. And we explicitly set the exclusive parameter to true, which means that figures are only simulated by the robot, and therefore no other TVB direct connections between the brain and fingers are going to be functioning. So this is what more or less the important features of the code of the TVB engine that will plug in with the robot. Yeah.
Yes, so a bit more technicalities about the TVB engine itself. So in order to exchange data between the two engines, we use so-called data packs, which are essentially pieces of data with some metadata that allow to identify them. And in the TVB engine, we use 4 data packs, 2 input and 2 output data packs. The 2 input data packs are basically positions of the left and right index, respectively. And the 2 output data packs are reference positions for these fingers. And if we want to get the positions from the previous iteration from Gazebo engine, then we just have to call a method of the engine class, just get data packs, and this returns us a Python dictionary with all the positions of the joints in the finger. And similarly, if you want to set the reference positions for the next iteration, we just have to call a proper method, which is called setDataPack, and we pass a dictionary of positions into there. And this is it. Next slide, please. And this is an example of a transceiver function that we use in the experiment. I don't want to go into details here, but what is happening here is that the transceiver function receives data of all the joints from the 2 index fingers of 2 hands, and it kind of converts it into 2 data packs for simplicity. So 1 data pack for the left index finger and 1 data pack for the right index finger, and these data packs will be sent to the TVB engine, and they will be accessible by the TVB engine. We also do some range conversion of the positions that the TVB sensor region can understand them immediately.
Right. And this is the actual loop of the simulation on the TVB side, where you can see more or less the same steps that we discussed during the synchronization between TVB and spiking networks. So there are communication instances from TVB to the fingers here that we call a motor command, and then also from the finger's proprioceptive input towards the TVB simulator. These updates then happen in both directions, and then we simulate one time step. And then this loop will continue for the whole simulation. So you see that we have to exchange instances of simulating with instances of exchanging data. Yeah, and in the end, you can see the result. First, we're going to show you a short video of the two fingers starting on the antiphase or parallel way of simulating, and about in the middle as they go faster. At some point, there is some critical fluctuations, and then they switch to the, actually, maybe I didn't start from the, yeah, okay. So when it gets faster, there are some fluctuations and it switches to the different kind of synchronization. Unfortunately, in the video, it's not very clear this, but you're going to see that on the time series. So here on the first panel, you see the positions of the fingers normalized in green and blue. And you see that on 3 frequency plateaus. And as the frequency changes, the amplitude decreases. So you can clearly see the 3 frequency plateaus here. And in black, you see the relative phase of the movement normalized with pi. So here it is pi, which means antiphase. And here is about 0, which means 0 phase, so in synchronization. And you can see the transition happening already at the beginning of this middle critical frequency plateau. And if we look at the window, time window before the transition and time window after the transition, you see here the antiphase mode of synchronization. Whereas here, everything, all motor and sensory and figure time series, they're all synchronized in phase. So that was pretty much, but Christoph?
Yes, so apart from interfacing TVB only with Gazebo, we also tried interfacing TVB with OpenSim using an RP core. And this is an example of like a very simple proof of concept where the TVB provides motor commands to the musculoskeletal model in OpenSim. So it's not really interesting from a scientific point of view, obviously, but it's a proof of concept that we can interface TVB with many different simulators. And yeah, I think it's promising.
So for future work, we are now in discussions to see how we can extend this project, either on the technical side or on the scientific side as well. The point is that by interfacing TVB with a robot and potentially also with a spiking simulator like Nest, we can actually model all the different levels that are involved, from movement of limbs to motor neurons, or specific systems that transfer the movement up to the whole brain, and compare with empirical data at all scales, from EMG to the brain neuroimaging data. And this offers us a virtual experimental platform where we can test perturbations or lesions and produce predictions of how this would be reflected in behavioral experiments. And therefore, we can perhaps in this case, for instance, of bimanual coordination, test more hypotheses on the underlying neuromuscular constraints that lead actually to these behavioral phase transitions. But obviously, there are many other applications we can envision, and we're going to see in the future what direction we're going to take. That was all.